In this video, we will explain matrices and the operations that we can do with matrices. Let me start by saying that an n by n matrix is an array of numbers, array of, let's say, n by n numbers. But the way they are arrayed forming n rows and n columns. We have n rows and n columns. This is an example of a 2 by 3 matrix. Then we need 2 rows and 3 columns. This will be 2, 3, 4, 1, -1, 5. When we have a matrix, we usually denote a matrix with a capital letter. And since we have 6 numbers, we're going to call these numbers according to its position. For example, the number 4 here, we call it little a 2, 1, to indicate that this is the number that is in the second row and first column. And also we will be denoting it like bracket and 2, 1. And this is one way to denote the numbers. Then, for example, if I ask what is a of 3, 2, then this will be row 3, column 2. This will be number 5. This is also denoted like a of 3, 2. Then we have the definition of matrix. What is a column vector? Column vector of size m. This is just an m by 1 matrix. Then, for example, a column vector of size 4 would be something like 2, 3, -1, 4. This is a column vector of size 4. What can we do with matrices? If we have a matrix, let's suppose I have this one, and I have a number, I can multiply a number with a matrix, and that's called scalar multiplication. Scalar multiplication. And this is the product of a number. Let's say if we have number 7 times a, where a is this matrix, it will be 7 times 2, 3, 4, 1, -1, 5. And then here we will get, the way to do this operation, we get a matrix of the same size. Remember, this is a 3 by 2 matrix. And then I will get a 3 by 2 matrix. What is that matrix? Each entry, I multiply each entry by the scalar. Then I get 14, 21, 28, 7, -7, 35. That's the way to multiply a number by a matrix. Notice that this applies also for the vectors. If I have like 2 times this vector, 2, 3, -1, 4, then I will get the vector 4, 6, -2, and 8. Then this is the scalar multiplication, and it takes any matrix. You need a matrix and a number, and you will get another matrix. This is a scalar multiplication. Another operation that we have for matrices is the sum of matrices. This one requires some conditions, and the conditions is that if we have 2 matrices and you want to consider the sum of the 2 matrices, they must have the same size. Then this must be an m by n, and this also needs to be an m by n. And the sum is the matrix C, which is again a matrix of the same dimension. How do we do the sum of 2 matrices? Let's suppose I have 2, 1, negative 1, 0, 1, 7, plus 3, 2, 1, 5, 1, 3. In this case, we have a 2 by 3 matrix and a 2 by 3 matrix. And then the sum is going to be also a 2 by 3 matrix. If the matrices don't have the same size, then you just say the sum cannot be done. And here we will get the matrix 5, 3, 0. I just add entry by entry. Here it will be 5, 1 plus 1 is 2, and 7 plus 3 is 10. This is the sum of two matrices. Please do this homework. With this notion of scalar multiplication and sum of matrices, I can define a linear combination, the notion of a linear combination of vectors. Let me just write that. Linear combination of vectors. And in order to talk about a linear combination of vectors, we need to have vectors of the same size. Let's suppose that we have the vectors v1 equal 2, negative 1, 4, v2 equal 3, 2, 1, and let's say v3 equal 1, 0, 1, and v4 equal 2, 3, 0. If we have four vectors of the same size, right, and in this case, to define the linear combination, we're going to care about the order, vector 1, vector 2, vector 3, and vector 4. Then a linear combination is a vector of this form. You have a number, let's say 3 times v1 plus 1 times v2 plus 2 times v3 plus 4 times v4. Then when you do the scalar multiplication of a number with vector 1 plus the scalar multiplication of another number with vector 2 plus the scalar multiplication of a number with vector 3 and so on, then you get what is called a linear combination of these vectors. Some notation here is that these numbers are going to be called the weights of the linear combination. And then in this case, this would be 3 times 2, negative 1, 4, plus 1 times 3, 2, 1, plus 2 times 1, 0, 1, plus 4 times 2, 3, 0. Remember, this is just the vector 6, negative 3, 12, plus 3, 2, 1, plus 2, 0, 2, plus 8, 12, 0. And then in this case we get 9, 10, 19. Here we get negative 1, 11, 12, 14, 15. In general, if we have, let's say, b1 up to bk, k vectors of size m, and we have numbers, let's call them numbers lambda 1, lambda k numbers, then these numbers are called the weights. Then the linear combination is the vector lambda 1 b1 plus lambda 2 b2 plus lambda k bk, and this is a vector of size m. Right? That's the notion of a linear combination. Please do this homework. Let me explain some notation that we're going to be using. We're going to denote the standard basis. Let's call it standard vectors by now. Standard vectors and standard vectors for vectors of size n. In general, let me denote Rn. This is the set of vectors of size m, n. That means that these vectors are like x1 up to xn, such that each one is a real number. Then here we collect all the vectors. Rn is the collection of all the vectors of size n, where each of the entries are going to be real numbers. Sometimes we will be talking about complex numbers too, but then in this case it's just Rn. Then the standard basis is going to be this vector e1 equal 1, 0, 0. e2 is 0, 1, 0, and so on. And then we get until en equal to 0, 0, 1. This is the standard vectors in Rn. As an example, the standard vectors in R2 would be 1, 0, which is e1, and e2 would be 0, 1. In R3 we have the standard vectors would be 1, 0, 0 for e1. For e2 we have 0, 1, 0, and for e3 we have 0, 0, 1. Notice that we can connect the notion of linear combination with the standard vectors. Then, for example, if we have the vector 3, 2, 1, this is a vector in R3, right? Vector in R3. And I can write this vector as a linear combination of the standard vectors. I can see that this is 3 times the vector 1, 0, 0, plus 2 times the vector 0, 1, 0, plus 1 times the vector 0, 0, 1. Then we are using the notion of a linear combination, right? Linear combination. Please do this homework. Now I'm going to proceed with the operation of matrices. And in this case, I'm going to define the product of a matrix with a vector. But again, this product is, in order to do the product, you need to have the right dimensions. Let me write down. Product of a matrix with a vector. And in this case, we have the matrix A and the vector B. But in this case, in order for this product to make sense, this matrix has to have dimension m by n, and this vector must have dimension n by 1. This is a vector of size n, and this is a matrix m by n. Let me do an example. Let's suppose that we have the vector 3, 2, 1, 0, 1, 4. This is dimension 3 by 2, and then I need a vector of dimension 2 by 1, a vector of size 2, let's say 2, negative 1. By definition, this product, what you do is you do a linear combination of the columns. And in a linear combination, I need the vectors. How many vectors do I have? I have 2 vectors, 2 columns, and I need 2 weights. What are the weights? These elements in the vectors. Then in this case, by definition, this product is 2 times 3, 2, 1, plus negative 1 times 0, 1, 4. And then we get something. What vector do I get? I get the vector 6, 4, 2, plus 0, negative 1, negative 4. And then this is the vector 6, 3, negative 2. Then this is the product of a matrix with a vector. In general, if we have a matrix of dimension n by n, then we have a matrix like A11, A12, A1n, A21, A22, A2n, and then here the m column would be M1, AM2, and then AMN. This is a matrix of dimension n by n, and we have a vector of dimension, let me just write it like this, this is A, and then we have a vector of dimension v n by 1, then we have a vector like, let's say, b1, b2, bn. Then by definition, this product is the linear combination of the columns of the matrix A using as weights these numbers. Then I will get B1 times this column, which is A11, A21, AM1, plus B2 times A12, A22, AM2, plus Bn, A1n, A2n, and then AMN. Notice that this is a vector in how many, what is the size of this vector when we do this? This is a vector with size m. Then this is the product of a matrix with a vector. Please do this quiz. Before explaining the product of two matrices, I would like to explain the notion of function and the notion of composition of functions. Let's go back to functions. Let's suppose that we have a function, we have a set 1, 2, 3, and let's suppose that we have a, b, and we have a function f. Then let's suppose that this is our function, right? Here we write f of 1 equal a, f of 2 equal b, and f of 3 equal b, right? We have a function, and let's suppose that this is the set. Sometimes we write this f from the set x to the set y. What is the set x? X is the set 1, 2, 3. This is usually called the domain of the function, and the codomain is, in this case, is AB. Let's suppose we have another function g from y to c. Let's suppose that this is the set AB, and c, let's suppose that this c is the set star, circle, and apple. Right? Let's suppose that the function g is defined by this is a star, circle, and apple, and let's suppose that this goes here and this goes to the apple. Then we have that in this particular example, g of a is this, and g of b is the apple. Then something that we can naturally define is the composition of the two functions. Let's call the composition the function h. Notice that something that is interesting about the notation is that even though we write the composition of f and g here in the picture, we write this composition as f composed with g. And the definition is that h of an element, let's call that element x, is just g of f of x. That means that first the function f acts on x, and you will get an element here, and then g acts on that output to produce another one. Then what would be the composition evaluated at 1? Then 1 goes to a, and a goes to star. Then we have this. What is h of 2? H of 2, 2 goes to B, and B goes to apple. And we have this. And H of 3 would be F takes 3 into B, and B takes B into apple. Again, this is the composition of two functions. Please do this quiz. One observation is that we have defined, we have defined the product of a matrix with a vector. Then let's suppose that we have this matrix A. Let's say 2, 1, 0, negative 1. And let's suppose that we have the vector V equal 1, negative 1. What is A times B? By definition, is the linear combination of the columns 2, 0, and 1, negative 1. What do I use as weights? These elements here, 1 and negative 1. Then I get the vector 2 minus 1 is 1, and here I get 1, 1. Notice that we can think about a function. That function, I'm going to call it T of A. This function, it goes from R2 into R2. And this function, let's suppose that this is my R2, and this is my R2. This function takes any vector here, and is sent it to A times B. In particular, for example, what is T, if for this particular example, T of A of this vector, 1, negative 1, it goes to 1, 1. Then this transformation, I can visualize it like this. It takes, here we have the domain of the transformation, which is R2, and here we have the codomain of the transformation, which is R2, and here we have the transformation T of A, because this transformation is coming from this function, from this matrix. Then this transformation takes the point, the vector 1, negative 1. 1, negative 1 is something like here, 1, negative 1. It takes this point, we can think this as a point or as a vector, and it sends it to 1, 1. This is, if this is B, this is T of A of B. Let's suppose what happened with this vector. This is the vector E1. E1 is the vector 1, 0. What is T of A of 1, 0? Sometimes we omit the two parentheses. Technically we need two parentheses, but we just say T of 1, 0. By definition, this is just 8 evaluated at 1, 0, which is 2, 1, 0, negative 1 times 1, 0. This is a linear combination of the columns 2, 0, and 1, negative 1. What do I use as weights? I use a 1 and a 0. What do I get? 2, 0. That means that this vector, this point here, goes to this point here. Maybe it would be a good idea if I use colors. This point goes to this point, and this point here goes to this point. What is the effect of E2? What happened with E2? E2 is 0, 1. When I do T of A of 0, 1, it would be A times 0, 1, which is 2, 1, 0, negative 1 times 0, 1. And by definition, this is a linear combination of the columns of A. What do I use as weights? This number 0 and 1. Then I get 1, negative 1. Then this will go to 1, negative 1, 1, negative 1. This point will go to this point. Then you can see that if you have something here, a collection of points, this collection of points will go to a collection of points in here. It's not difficult to show that, for example, if you consider this triangle, points that are in this triangle, they will go to points that are in this triangle. And it translates this triangle into that triangle. That is called the transformation, the function associated with a matrix. Please do this quiz. In general, if we have a matrix, of dimension, let's suppose that we have a matrix A, and the dimension of this is m by n. Then it makes sense to multiply this matrix with a vector n by 1. And you see that you will get a vector in Rm. That means that if you have a matrix n by n, that matrix defines a function from the domain would be vectors in Rn, and it will produce a vector in Rm. In the same way, you take a vector here, this is the input, and the output is just A times B. Please do this quiz. For the last two questions, it will be useful to see the rest of the video. Now, let's think about the composition of two functions. Let's suppose that you have a function like this that comes from a matrix Rn into Rm, and let's suppose that you have another function that comes from a matrix, and let's suppose that it comes from Rm into Rk, right? Then it makes sense to talk about the composition of these two functions. How do I write the composition? I write like T of A composed with T of B, right? First, at T of A, it takes a vector in Rn, you get a vector in Rm, and then T of B takes a vector in Rm into a vector in Rk. Then this is a function from Rn into Rk. Then we will see that this is equal to a transformation of a matrix 2 that comes from a matrix. What matrix would that be? How can we get the matrix? How do I get the matrix? One way to see it is, first, let's try to think how to find a matrix if we know the effect of some vectors. Let's suppose that we have a transformation from R2 into a transformation from R2. And let's suppose that I know that this is the vector 1, 0, and the 1, 0 goes to, let's say, 2, 1, and 0, 1 goes to, let's say, 1, negative 1. If I know that this function is the T of a matrix, what is the matrix? This function is T of a matrix. What is the matrix? I know that T of 1, 0, this matrix has two columns, is A11, A12, A21, and A22. And I know that it sends 1, 0. What is TA of 1, 0? This is a linear combination of the columns A11, A21, A12, A22, and here we have to use the weights 1 and 0. That means that this is A11 and A21. That means that if we know that this vector 1, 0 goes to, if this is TA of 1, 0, then this is the first column. Then E1 will go to the first column, and then I know that A would be the vector 2, 1. And the same argument shows that if 0, 1 goes to 1, negative 1, the second column should be 1, negative 1. Then, if we know that a transformation comes from a matrix, then to find the columns, it's just enough to know where the standard basis goes. And the rule is E1 will go to the first column of the matrix, and E2 will go to the second column of the matrix, and so on. Then, in order to solve this problem, to find C, I need to know where E1 goes. Let's find the first column of C. First of all, C defines a transformation from Rn to Rk. That means that it makes sense to talk C times V, and this V is an n by 1 vector. And I know that the output is K. Then this matrix should be a K by n matrix, so that this vector makes sense. And then let's see what is TOC. TOC of E1, by definition, is the composition is T of A composed with T of B of E1. But this is T of B, this is the matrix B times, and this is A of E1. But what is A of E1? A of E1 is just the first column of the matrix A, which is A11, A21. The matrix A has dimension, the A has dimension m by n, then here is AM1. The matrix B is a matrix of dimension k by m. Then, by definition, this is just A11, a linear combination of the columns. What are the columns of B? B11, B21, and we have K rows, BK1, plus AM1, and here we have B, BM, B1M, B2M, and BKM. Then the first column of C would be the vector, when I do the first column, it would be B11, A11, plus B1M, AM1. This is the entry 11, and then I will do B21, A11, plus here B2M, AM1, and then the last entry will be BK1, A11, plus BKM, AM1. And with all of this, you end up with the matrix C. The notation of this matrix C, you can do the other column, the other columns, and this matrix C by notation is denoted like the matrix B times A. Remember that the dimension of A is m by n, and the dimension of B is k by m, and the dimension of C is k by n. Then all of this argument shows that if you want to define the matrix of the function that comes from the composition of functions, then you will end up with something that you would do with the entries of A and B. And the key part here is that in order for the product to make sense, in order for the composition to make sense, then you need to have that the number of columns of the first factor must be equal to the number of rows of the second factor. And the matrix would be of dimension k by n. It's like if this m cancel out and you get k by m. Let's practice what we get when we do the product of two matrices. For example, you can have the product of this matrix times this matrix, 2, 1, 1, 1, 3, 2. Let's see, here, this is a matrix of dimension 2 by 3, and this is a matrix of dimension 3 by 2. Then the product will be a matrix of dimension, you cancel this, and you get a matrix of dimension 2 by 2. How do you do that product? The product is done by something like this, but essentially what you do to find the entry 1, 1. What do you do to find the entry 1, 1? You place your left hand in the first row of the first matrix. This is the entry 1, 1. And you place your right hand in the first column of the second matrix. First row of the first matrix, first row of the second matrix, first column of the second matrix, and you start multiplying. 2 times 2 is 4, and then you move this hand to the right and this one down. Then it's 4 plus 3 times 1 is 3 plus 1 times 3 is 3. That means that this number here is 10. Notice that we have a 2 by 2 matrix. Let's see this, what entry, let's see what comes in here. What entry is this? This is the entry 2, 1. That means row 2, column 1. How do we do this? Row 2, that means that we pick the second row of the first matrix and we pick the first column of the second matrix, and we do that procedure. We place our left hand here, our right hand here, we start multiplying and adding. 8 plus 1 is 9, minus 3 is 6. That is what comes in here. What comes in here? This is the entry 1, 2. Then that means that I place my left hand in the first row of the first matrix and my right hand at the beginning of the second column of the second matrix, and I start multiplying and adding. I have 2 plus 3 is 5 plus 2 is 7. One number comes here. This is the entry 2, 2. This is the entry 2, 2. That means that I use the second row and the second column. Then I do 4 plus 1 is 5 minus 2 is 3. Okay, let me just finish doing another example of this, and then we stop here. Let's suppose that we have something like 2, 3, 1, 4, 1, 7, 0, 2. This is a 4 by 2 matrix, and let's suppose I have a 2 by 3 matrix. 1, 0, negative 1, 0, 0, 1, 0, negative 1, 2. Sorry, 2 by 3 matrix. That means something like this. Then this product is going to produce, this product can be done because the number of columns of the first matrix agrees with the number of rows of the second matrix, and the product will be a matrix of dimension 4 by 3. It's like if you cancel these two here. Then we have a 4 by 3 matrix. That means that we have 1, 2, 3, 4. And then we have to find 12 numbers. Let's see, how do I find, for example, this number here? What is that number? This is the entry 4, 2. Right? This is the entry 4, 2. That means that I use the fourth row and the second column of this. When I do this product, 0 times 0 is 0, plus 0 is 0. This number is 0. But let's go in order. This is the entry 1, 1. That means that I use the first row and the first column. When I do 2 times 1 is 2, plus 0 is 2. What comes in here? This is the entry 1, 2. That means that I use the first row and the second column. Then I will be just 0 plus 0 is 0. what number comes here? This is the entry 1, 3. 1, 3 means that I use the first row and the third column. Then it will be negative 2 plus 3 is 1. What number comes here? This is the entry 2, 1. That means that I use the second row and the first column, and I do 1 plus 0 is just 1. For this one, I use the second row and the second column, and then I will get 0. For this one, I use the second row of this matrix and the third column, and I will do 1 times negative 1 is negative 1 plus 4 is 3. And for this one, this is the entry 3, 1. 3, 1, that means that I use the third row and the first column. I will do 1 plus 0 is 1. And here, this is the entry 3, 2, third row, second column. I will get 0. And here, this is the entry 3, 3. I use the third row and the third column. I do 1 times negative 1 is negative 1 plus 7 is 6. This is the entry 4, 1. I use the fourth row and the first column, and I get 0 plus 0 is 0. This one we already did it, and this is the entry 4, 3. That means that I use the fourth row and the third column. 0 plus 2 is just 2. Okay, this is in general how we do the product of matrices. Please do this quiz. Then I would like to stop here.